what I wanted to do was show you how trade studies can be set up. Of course, we now want to understand how to analyze all these different architectures and come to some conclusion as to which one to pick in terms of what our payload is really going to be when we launch this satellite. So we can edit trade studies over here. That's a button that it's in the lower left there. And there's a whole bunch of trade studies that you can invoke with this software. And one of the things we did as part of the SBIR was allow you to specify as many architecture and fidelity levels as you want for each trade study. So if I do a design of experiments, for example, like this one, this is the one we're actually going to do, I can do the design of experiments across all these, whatever the design of experiments is, across all these architecture/fidelity levels. So in this case, I'm doing basically varying the geometry, the size factor, from some low value to some high value. It was done for more levels than that, but you can go in there and change that number if you want to. And then the output is the accuracy, the cost, the weight, the power, and also the signal to noise ratio. We'll just be looking at these first four. So I can hit the Run Trade Study button here. It's all set up. I can hit the Run Trade Study button. It'll run. I don't want to do it because it'll take several minutes to finish, but I do have the results pre-recorded. Just so you know, there's other types of trade studies you can do. There's a manual input, for example, which is just basically you set up your own points that you want to run. There's optimization, there's probabilistic analysis, and there's also a couple of new ones that we did for this SBIR. This is design of experiments with probabilistic analysis within the design of experiments. So if you want to basically do something like vary the design and understand the variance of some output variable, you would want to, each point would then be accompanied by a probabilistic analysis to get the variance of that output, and you would proceed to plot the result accordingly. Same thing here, optimization with probabilistics inside. If you had a probabilistic, a statistic basically that you wanted to optimize against, let's say you wanted to minimize the variance of something, you could do that as well. But let's stick to the design of experiments here. That's really the most interesting because we're trying to select, we're doing an analysis of alternatives here. I already have these results. They are in a tabular format. Let me show you that. So it's just a table with our accuracy, our cost, weight, power, and signal to noise ratio as a function of this single size factor across all the different architectures. So if you scroll across the top here, you'll see that we have the results for the FLIR, the infrared camera architecture. If you keep going, you'll see that there's results for the synthetic aperture radar. And then if you go all the way to the end, there's the results for the combination infrared camera and synthetic aperture radar together. So if we hit the graph results button here, we can basically graph what we're interested in. So we're interested in the accuracy, so this is just the x-axis is always going to be the same. It's the size factor. And then we'll create some graph. Well, first graph would be accuracy. We'll add another graph to plot the cost. Wrong one. That's the cost. Then we'll add another one for the power consumed by the sensor, and another one to reflect the weight. So what we see here, basically, the green one is the combined architecture. That's both the infrared camera and the synthetic aperture radar. The blue one is the synthetic aperture radar alone, and the red one is the infrared camera alone. But let's say we have a requirement that we want an accuracy of 90%. So this is our line. Okay. So for the combined payload, we would get, we would need a size factor of about 0.9. It can be smaller than nominal. For the synthetic aperture radar, we would need a size factor of about 1.6 to get an accuracy of 90%, maybe a little less than 1.6. but let's call it 1.6. For the infrared camera, you would need a size factor of 2.6. Okay, so you can use a much smaller sensor package for the combined instruments than for either the synthetic aperture radar or the infrared camera. Alright, so for cost, however, it costs a lot more to have two instruments than one of each, as you can see here. Okay, so even at the smallest one, for the combined one, if I compare this, that's still a lot more expensive than what I would need for the synthetic aperture radar or what I would need for the infrared camera. However, it does beat the others. The combined instrument beats the others in terms of cost, or power, I should say, and weight. Okay, so because we can use a much smaller instrument, we get better power and better weight, but not by much compared to the synthetic aperture radar. I have a better picture of this, by the way. Okay, so there's the annotated final results. So we're comparing, basically, because we have a requirement of 90% accuracy, we're comparing the 0.9 size for the combined sensor combination, 1.6 for the synthetic aperture radar, and 2.6 for the infrared camera. So for cost, the infrared camera is the winner. These are the costs, so it's $1.3 million. The synthetic aperture radar is $1.7 million, and the combined is $2.4 million. So it's a lot more expensive to combine the instruments, but you get better power. You get 512 watts versus 648 watts versus 1,173 watts for just the infrared camera, and you get better weight. You get 156 pounds versus 168 pounds versus 419 pounds. So you have a decision to make, right? You can either, if you have the budget, you might want to pick the combined instrument, pack as a small combined one because that really does give you better power and weight, or you could opt to, for a medium architecture, just the synthetic aperture radar, because it doesn't do that badly. It costs a lot less, but it doesn't do that badly in terms of power compared to the best one, or in terms of weight. It's just slightly heavier and moderately more power consuming. So that's the analysis.